Hi guys, today we're going to talk about coffee cup calorimetry. This is calorimetry that involves solutions, not solids. Previously, we had done equations where we dropped like a hot metal into a cup of water. This is going to be a little bit different. This is when solutes dissolve in aqueous solution. They can either release or absorb heat. Okay, so remember that releasing heat makes something exothermic. To absorb heat is endothermic. It's called coffee cup calorimetry. Think of like a styrofoam cup that can hold and insulate a heat reaction, but it's going to be at constant pressure. Okay, so today we want to first remember that the heat absorbed by an endothermic reaction has to come from the water in the aqueous solution. So the heat, Q, of the reaction, if it's endothermic, means that it's a positive Q. But that heat has to come from somewhere. Remember the law of conservation of energy. Heat absorbed equals heat released. So the Q of the water has to be negative. So if the reaction absorbs heat, it absorbs that heat from the water so that the water's temperature will go down and that reaction will feel cold to the touch. The opposite is also true. If the heat released by an exothermic reaction has to come to the water, okay? So if the reaction is going to release that heat, it's going to be going out into the water in the aqueous solution. Therefore, the Q of the reaction will be negative because it's exothermic. But flip the sign, the Q of the water in that solution will be positive so that the temperature increases and that one will feel hot. Okay? So our first example of this kind of coffee cup calorimetry math is if we have a 15-gram sample of calcium chloride and we're going to dissolve that in 250 milliliters of water at 25.2 degrees Celsius in a coffee cup calorimeter. The temperature increases to 37.5 degrees Celsius. Calculate the enthalpy change, that means delta H, for the dissolution of the calcium chloride in kilojoules per mole. Okay? So when we want to get to kilojoules per mole, that's our goal, right? I first need kilojoules and I'm going to need moles, okay? And then I'm going to divide those values. So let's first start by getting our kilojoules, okay? What you have to remember about the enthalpy change of a reaction is that it's going to equal the heat of that reaction divided by the moles, right? That's where this kilojoules per mole is going to come from. But that Q of the reaction is going to equal the opposite sign, negative Q, of the water that we're actually measuring the temperature of. Okay? So this means that I'm going to use MCAT when I have Q, and I want Q of the water. So the water is 250 milliliters. But don't forget, right, that the density of water is 1 gram per milliliter. That means if I have 250 milliliters, I have 250 grams. Okay. So when I start my problem here, I'm going to use for my mass that 250 grams times the specific heat of water, which we know to be 4.18 joules per gram degrees Celsius. That in parentheses as well. Times the change in temperature. So our change in temperature here is going to be that 37.5 minus that 25.2. So final minus initial. the temperature increased. So we're going to have a positive 12.3 degrees Celsius. So my grams cancel, my degrees Celsius cancel, and I'm left with joules. So 250 times 4.18 times 12.3 is negative 12,853.5 joules. That's a lot of joules. So we can easily make that kilojoules by moving our decimal place over. And really, I only need 3 sig figs. Well, I'm going to leave it 4 for right now. We can change it here in a minute. So those are my kilojoules for my heat of reaction. Right? That's my Q reaction in kilojoules. But I need to divide that per mole of what I'm dissolving. So my solute is that 15 grams of calcium chloride. So I need to take my 15 grams of calcium chloride and use molar mass to find those moles. Calcium weighs 40.08 plus 2 chlorines, 2 times 35.45 is 110.98 grams per mole. So 15 divided by 110.98 is 0.135 moles. If I know my kilojoules and I know my moles, I can get my kilojoules per mole by dividing these two values, right? Negative 12.85 divided by 0.135, that's going to equal a negative 95.2. I'll fix my sig figs here. Kilojoules per mole as my delta H value. Okay. So things that are slightly new to us are just the word enthalpy, because we already knew that Q of anything is equal to MCAT. We already know how to go from grams to moles, but then to get those kilojoules per mole in that delta H, knowing that this is kilojoules that we can get from that water and that our moles are from the solute, that reaction will give off 95.2 kilojoules for every mole of calcium chloride that you use. Okay. Let's do a second example. Okay. Let's say we have, scoop this up, 12.5 grams of ammonium chloride is dissolved in 50 milliliters of water at 24.4 degrees Celsius in a coffee cup calorimeter. The temperature decreased to 21.6 degrees. Calculate the enthalpy change in kilojoules per mole. Okay, so again, we're finding enthalpy in kilojoules per mole. I know that enthalpy of any reaction equals the heat of that reaction divided by the moles of the solute that is doing the reaction, right? The actual reactant part. So again, Q of the reaction equals the opposite sign of the water. Okay. I know that the Q of water is going to equal its MCAT. Again, 50 milliliters is the same as 50 grams of water. And my change in temperature this time, final minus initial, 21.6 minus 24.4 is a negative 2.8 degrees Celsius. The water's temperature went down. Okay? So 50 times 4.18 times 2.8, my negatives cancel. That's going to give me 585.2 joules. But I don't want joules. So my reaction said I needed kilojoules per mole. So 1, 2, 3, that equals 0.5852 kilojoules. Now the only thing I'm missing here are my per mole. So if I have 12.5 grams of ammonium chloride, nitrogen weighs 14.01, 4 hydrogens at 1.01 each, plus a chlorine, which is 35.45. Ammonium chloride weighs 53.5 grams per mole. So 12.5 divided by 53.5 equals 0.2336 moles. So then delta H is kilojoules per mole. When I combine these two, 0.5852 divided by 0.2336. I guess I only needed 3 sig figs here again. It's going to be a positive 2.51 kilojoules per mole. For my last example, we're not going to find the enthalpy this time. We're actually going to be looking for a different variable. Okay. So in our last example, we'll be given 9.75 grams of sodium hydroxide that is dissolved in 100 milliliters of water at 22.7 degrees in a coffee cup calorimeter. If the change in enthalpy is negative 44.5 kilojoules per mole, what is the expected final temperature of the solution? Okay, so this time we're looking for final temperature. So this is a very different, not very different, but a different kind of question. Right? So this time I know that the delta H of the reaction is negative 44.5 kilojoules per mole, but I want a final temperature. So to get final temperature, I'm going to have to use MCAT, which means I need Q. So from my delta H of my reaction, I need to get rid of moles and get those joules so that I can find my value of Q, the heat. So the first thing I'm going to do this time is the last thing I did last time, right? I'm going to use this 9.75 grams of sodium hydroxide and find those moles. Sodium weighs 22.99 plus oxygen weighs 16 and hydrogen weighs 1.01. That is a nice even 40 grams per mole. That's going to give me 0.244 moles. So if I know that I only have 0.2 moles, but I know every mole would give me this much heat, I'm going to multiply those together so that the moles cancel, and I'll be left with kilojoules. So 0.244 times my negative 44.5 is negative 10 10.89 kilojoules. Not 89, 86. I ran out of space. Negative 10.86 kilojoules. But I don't want kilojoules because I need to use Q, right? Q of that reaction needs to get to Q of water so that I can use the change in temperature of the water, right? So I need these kilojoules to be in joules. So I'm going to move my decimal place back 1, 2, 3. And that's going to be 10,860 joules as my heat of the reaction, right? But remember that heat of reaction is the opposite sign of the water. So if the heat is releasing that much, that means the water has to absorb that much. So if this is negative 10,860, then the heat of the water is a positive 10,860 joules. Okay. Now, because I know my Q of the water, I can then use mass C and delta T of water to find that final temperature, right? So my 10,860 equals the mass of my water was 100 milliliters, which is 100 grams, times the specific heat of water. I don't know the final, but I know the initial temperature was 22.7 degrees. Therefore, I can either simplify and get rid of or get rid of in different steps, but do algebra to solve for my final temperature. What I'm going to do is divide by 100 first because that is just moving the decimal place back, 1, 2, right? To get me 108.6 equals 4.18 times TF minus 22.7. I'm not going to distribute because that seems like a waste of time, so I'm also going to divide by 4.18. That gives me 25.98 equals TF minus 22.7. So now to get rid of the minus 22.7, I'm going to add 22.7 to both sides. And that temperature goes up to 48.7 degrees Celsius as my final temperature. Okay. I hope these example problems helped you understand some coffee cup calorimetry.